Hello everyone, welcome to Generative AI from Scratch. I'm Daksha Subramanya and I'll be your teacher today. We'll start off this course with Gen AI fundamentals where we will talk about LLMs and embeddings and we'll discuss vector DBs and we'll talk about RAG, that is Retrieval Augmented Generation, and then we will proceed to LangChain Framework and we'll also see how to build LLM apps in Python. So here AI splits into two camps. One is non-generative AI and the second is generative AI. So non-generative AI deals with decision-making problems. Let's say you have a chest X-ray and you have to see if the patient have pneumonia or not, or you have a credit history and you are deciding whether they should get a loan or not. So in these problems, you're not creating anything new. You have data and you're making a decision based on it. But generative AI is different. Here you are generating content. The classic example is ChatGPT. So it can write your resume, plan a trip, or create an image of Hulk playing Gujarati Dandiya. The content that Gen AI generates can be text, images, video, audio, or you can decide what it wants to generate. So let us now talk about the evolution of AI. To understand where we are today, let us trace the path. So in the early days, we were solving problems like predicting home prices based on area, number of bedrooms, and age. This is statistical machine learning, and those input factors are called features. Then came more complex problems like identifying whether an image is a cat or a dog. Here, the features are things like whiskers or pointy ears, and the data is just a grid of pixels. It's unstructured, and the features are very messy. So, now let's talk about evolution of AI. To understand where we are today, let us trace back the path. In the early days, we were solving problems like predicting home prices based on area, number of bedrooms, and age. This is statistical machine learning, and those input factors are called features. Then came more complex problems like identifying whether an image is a cat or a dog. Here, the features are things like whiskers or pointy ears, and the data is just grid of pixels. It's unstructured and messy. The features are also variable, like the cat's face could be at a different angle and the ears in a different corner. The legs might not be visible at all. Statistical ML struggles here, and which is why we need neural networks and deep learning networks. So one of the most common architectures in neural networks is a recurrent neural network or RNN. In an RNN, you feed a sequence word by word. For example, to translate English to Hindi, you feed the first word and get a translation output, and then feed that output along with the next word back into the same network, and it creates a loop, a recurrence, and hence the name. This was used heavily for language translation. But then another problem generated. The problem was you have seen Gmail's autocomplete, right? You start typing, let's say you start typing thanks for reaching out and it finishes the sentence for you. How does that work? So here the model reads the context. In this case, an email about a potential collaboration and predicts the next probability of the next word. Contacting me might have a probability of 0.91 and finishing the project would have much lower probability given the context. If you train a neural network on a huge corpus of text and have it predict the next word in a sentence, you get what's called a language model, an AI model that predicts the next word or set of words for a given input sequence. You can even generate training data for this automatically. Take a Wikipedia article on India's freedom movement and create fill in the blank exercises. First Indian nationalist to embrace dash. You generate thousands of these pairs, feed them into a neural network, and train it. No human labeling needed. This approach is called self supervised learning, and it's one of the reasons language models can be trained on such massive data sets. When you make that neural network very large, hundreds of layers, billions of parameters, and train it on enormous amounts of text, you get a large language model or an LLM. GPT-4, the model behind ChatGPT, has 175 billion parameters, and now GPT-5 has more than 1 trillion parameters. Every one of those parameters is a weight in the neural network. And the critical breakthrough that enabled all of this was a 2017 research paper called Attention is All You Need, which introduced a new neural network architecture called the transformer. This is what powers modern LLMs. From transformers, we have gotten a whole ecosystem of models. Google released BERT, OpenAI released GPT, the generative pre-trained transformer. For images, we have DAL-E and stable diffusion. You give text, you get an image. OpenAI Sora is a text to video model, and even Gemini VO3 is a text to video model. All of this became possible because of the transformer architecture. Now we will proceed to understanding LLMs. Let me give you an intuition for what an LLM actually is and isn't. Imagine a parrot named Buddy. Buddy has listened to every conversation in his owner Peter's house, thousands of hours of dialogue. When Buddy hears feeling hungry, I would like to have some dash, the probability of Buddy saying biryani is much higher than saying bicycle. He is predicting the next word based on patterns from past conversation. But here's the key. Buddy doesn't understand biryani. He has no experience of taste or hunger. He's working purely on statistical probability with some randomness thrown in. We call this the stochastic parrot, a system that produces language using probability and randomness, not comprehension. A language model works the same way. It's a neural network predicting the next word based on patterns learned from training data. Now imagine Buddy gets a superpower. He can listen to every conversation in every home, school, and university in the world. Suddenly, he can answer history questions, give nutrition advice, write poetry, and this is what makes a large language model large. It's trained on Wikipedia, news articles, books, code, and so much more, capturing enormously complex patterns across the entire breadth of human written knowledge. On top of statistical prediction, LLMs also use a technique called reinforcement learning from human feedback or RLHF. During training, human reviewers evaluate the model's output and flag toxic or harmful responses. The model learns to avoid those. This is how OpenAI made ChatGPT safer and more helpful. A large workforce of humans labeled which outputs were good and which were not. One important thing to keep in mind is LLMs have no subjective experience. They don't have emotions or they don't have any consciousness. They work purely based on the data they were trained on. Now, let us learn about two more concepts, embeddings and vector databases. When you search Google for calories in apple versus employees at Apple, how does Google know the first apple is a fruit and the second apple is a company? Well, it uses semantic search, not exact keyword matching, but understanding the intent and context of a query. The mechanism underneath is embeddings. An embedding is a numerical representation of text in the form of a vector, a list of numbers that captures the meaning of the text. Think of it like this. For the word apple, you might assign values to features related to phones, a location, and it has revenue, etc. But the same sequence of numbers is the word's vector. For example, for the word apple, the fruit, the same features would have very different values. When you look at the vectors, you can tell that the Apple, the company, and the Samsung are similar, but the apple, the fruit, and orange are similar, even without any keyword matching. This is powerful enough to do arithmetic on words. A famous example is Paris minus France plus India is equal to Delhi, or Apple minus Tim Cook plus Satya Nadella is equal to Microsoft. The math works because the vectors encode meaning. Now, when you're building a real AI application, you might have millions of these embedding vectors to search through. And that is where vector databases come in. In a naive approach, we store embeddings in a regular SQL database and do a linear cosine similarity search. This falls apart at scale. When you have million embeddings and a new search query, checking each one sequentially is computationally prohibitive. Vector databases solve this with techniques like locality sensitive hashing, which groups similar embeddings into buckets. When you search, you only compare your query vector against the vectors in the relevant bucket, not all million. This makes similarity search fast enough for production use. Popular options include Pinecone, Milvus, Chroma, VWeight, and Face. Face is a library from Facebook AI that works well for smaller scale use cases. And Face literally means Facebook AI similarity search. Now let us talk about RAG or Retrieval Augmented Generation. Say you want to build a ChatGPT like tool on your company's internal data. The internal data might include product documents, financial reports, customer records, but ChatGPT doesn't have access to any of that. So you have two options. First one is to fine tune the model, train it extensively on your data. This is like sending a student to biology school for a full year to become an expert. Option 2 is an open book exam. Let the student walk into the exam with the textbook. She doesn't need to have memorized everything. She's smart enough to look up the right section and write a good answer. RAG is option 2. When a user asks a question, the system retrieves the most relevant chunks from your private database and hands them to the LLM as context. The LLM reads those chunks and answers the question without ever having been trained on your data. This approach is faster, cheaper, and far more flexible than fine tuning. It's how most enterprise LLM applications are built today. Now, let us talk about the Gen AI toolbox. Before we dive into Python or before we go into code, these are the quick map of tools you'll encounter. What what are LLMs? LLMs are commercial models like GPT-4 and Google Gemini 3.1. These are the best performers but cost money per token. And open source alternatives include Llama, DeepSeek, Mistral. They are free but require more setup. There are also cloud services like Azure OpenAI, Amazon Bedrock, Google Cloud. These let you host models in a managed environment with data privacy guarantees. There are also frameworks like LangChain. LangChain is the most popular Python framework for building LLM applications. It abstracts away the model specific APIs so you can swap models without rewriting your app. Embeddings models and vector DBs are also in the Gen AI toolbox. So OpenAI embeddings, Hugging Face sentence transformers, Chroma, Face, and Pinecone. So now let's actually see how can we use these tools. Now we will talk about the LangChain, the framework behind LLMs. So what is LangChain and why does it exist? So when you use ChatGPT, you're calling the OpenAI API under the hood. If you wanted to build your own restaurant name generator, you could call that API directly. Simple enough. But here's the problem. What if the API costs become too high and you want to switch to an open source model like Llama? Or you want your app to pull from Google search or your company's internal database. Every time you add a capability or switch a model, you're rewriting code. LangChain solves this. It's a Python framework that wraps all these integrations, different LLMs, data sources, tools behind consistent APIs. Your code stays the same whether you're using GPT-4, Llama, or Mistral. You just swap the model configuration. So here are the core concepts. So first step is to create an LLM object when you're using a LangChain framework. So here in the LLM object, there is something called the temperature. So temperature parameter controls the creativity. 0 means it is predictable and safe. 1 means creative but potentially unreliable. Usually zero point 0.7 is a good middle ground. Then we use prompt templates. Instead of hard coding Indian into a string, we use a template like this. And then we use something called chains. A chain links a prompt template and an LLM together. So here you can see the code implementation of the chain. So let's say for an Indian, this is what it means. It is linked to Maharaja Palace. So this is a chain. And sequential chains let you pipe the output of one chain into the next. Like let's say generate a restaurant name, then use that name to generate a menu. The output of step 1 becomes the input of step 2. This is a sequential chain. Now let us talk about agents and memory. So agents give LLMs access to external tools. When you ask ChatGPT, find me flights from New York to Delhi on August 1st, it uses a plugin to query a flight search API because it has no real-time data on its own. That's an agent, an LLM using its reasoning capability to decide which tool to call and synthesize the answer. LangChain provides built-in tools for Wikipedia search, Google search via SERP API, a calculator, and many others. You configure an agent with a set of tools and it figures out which one to use based on the question. Memory allows chains and agents to remember the conversation history. So when a user asks who was the captain of the winning team after a question about cricket, the system knows what sport they mean and hence by default they answer about cricket. Lang chains are stateless. You attach a conversation buffer memory to give them memory. For production, you typically use a windowed version that only retains the last n exchanges, avoiding runaway token costs. So this is what we have learned today in this generative AI introduction class. So we learned about generative AI, which creates content which is mostly powered by transformers. We learned about LLMs and we met Buddy, our stochastic parrot, and we also spoke about embeddings, which is nothing but text represented as numbers. We also looked upon vector databases, which is fast semantic search at scale. Then we looked into LangChain Framework, and we also looked into agents and memory. So all the resources of this lecture, including the presentation, will be available in the description. And thank you for watching.